Unit 6, Chemical Reactions, begins us discussing things that everybody's wanted to probably talk about and actually look at more specifically in most every chemistry class, and that is, again, chemical reactions, because that's why people take chemistry, is to learn about the chemical reactions. A lot of the previous units have given us the background information for this unit to actually even be possible. Without that background information, the other stuff would be very difficult for us to understand. Because remember, back in Unit 1, we talked and described chemical reactions or chemical changes as in using an equation. We talked about the left and right, and the chemical equation has a reactant side, which is on the left, and then a product side, which is on the right. Those give us this kind of what goes into the beaker, what happens inside the beaker, or what comes out of it. The reactants are chemicals that are on the left-hand side. They are the stuff that's being reacted. Now, sometimes we have just two things on the reactant side, as shown here. There are also other times in that we have just one thing on the reactant side. That's just one thing reacting, which means something else is usually happening. Something's heating in it, or light is being shown on it, and it will go through a chemical reaction. If you remember back as well, and back in Unit 1, we actually talked about signs that a chemical reaction does even occur. So these are just the reactants. They are the left-hand side of the arrow. Now the products are on the right-hand side of the arrow. They're what's being produced. That's what's coming out of the factory, so to speak. You can think of the arrow as the factory. The reactants are on the left. That's the raw product going into the reaction. And then what comes out of the factory is the products, and that's what most factories produce, a product. They are the result of the chemical reaction, the result of. Now, sometimes there are multiple step ones where you will see the products of one being used for the reactants of another, but those are ones that we can look at, but at this moment in time, we're just looking at the generalization of what parts of the reaction we're looking at. Now, when we look at it, we can actually see reactions happening. We can observe what happens, as the reaction of taking sodium hydrogen carbonate and mixing it with acetic acid. Now, a vigorous reaction occurs, and equivalently, what we are actually just doing is taking baking soda and mixing it with vinegar. Now, a vigorous reaction can mean a lot of different things. It can be mixing baking soda and vinegar, but it can also be much more violent, but they can be still vigorous. Vigorous is how quickly things happen. So we do have to understand that, and even sometimes slow-moving reactions are worth the time that it takes for them to actually happen. So we can just observe what happens. And we did a lot of observing in our earlier units when we were looking at observing the chemical reactions happening. Now, the more complete description of what's happening is by telling what is being produced in the full reaction, and not actually just saying, oh, something happened, a reaction happened, gas was being given off. So what we want is a little bit more descriptive understanding. So solid sodium hydrogen carbonate plus aqueous acetic acid reacts to form a gaseous carbon dioxide, gaseous water, and an aqueous sodium acetate. That gives a very descriptive understanding of what's going on in that reaction. It's telling me that I'm using a solid version of sodium hydrogen carbonate, also known as baking soda, and acetic acid. Now, because a lot of times we're using vinegar as acetic acid, and vinegar is a 5% acetic acid solution, meaning the other 95% of it is actually just water, and that's why we call it aqueous or aqueous, is another pronunciation. Now, the bubbles and fizzing that happens, that is actually carbon dioxide and water vapor. Though what's left over is going to be your sodium acetate. Now, this sodium acetate a lot of times can be mistaken as part of leftover solid sodium hydrogen carbonate. And that's because not all of the sodium hydrogen carbonate is actually reacted. And that's what usually ends up being the solid left over. So we do have to be somewhat careful when we're looking at chemical reactions. Am I looking at leftover reactant, or am I actually looking at a product? And the idea of this unit and the actually this chapter and some of the following chapters is to give you some of the ideas, or at least the tools to decide what is actually looking at that. Now we can put this all into a chemical reaction, and what this means is we can write it all out to actually show, based on our understanding of naming that we talked about in the last unit. And so we can see that sodium bicarbonate, just again, it's another name of writing out sodium hydrogen carbonate, and acetic acid. Now this carbon dioxide and water are just, again, CO2 and H2O, and sodium acetate. And we can see that we have the acetate ion. We write our symbols and everything to identify and show. Now, I personally like writing out chemical reactions and using the symbols. I think it's a lot easier. It shows exactly the same thing. It's communicating the same information to somebody. But to me, it's a lot easier and shorter to write out the names and formulas and symbols, as opposed to maybe writing out the full name. Those can be a little bit cumbersome sometimes. Propane gas reacts with oxygen to produce water vapor and carbon dioxide. Choose the correct word equation for this reaction. Now, some of the symbols that we use are very important, and these symbols explain a lot of things. The addition sign shows and separates the reactants or the products from other parts of that side of the reaction. The yield, or the arrow, and it's usually always pointing from the left to the right, because that's usually how we write, is our yields. It separates reactants from the products. Another way we can look at it is that to yield, to make, to produce are ways in which that happens. We do not use these symbols as much, and the double-sided arrow is for reversible reactions. Now we might look at some reactions that are reversible, but a lot of times we won't look at actually those arrows, because the size of the arrow can actually indicate to somebody where which side occurs a little bit more often, as opposed to maybe some others. The S, the L, and the G designate reactant or product. It tells us what state it is found in. I normally will write my L's in more of a cursive L, so it's easier for us to understand which one I'm dealing with, and so that we don't confuse the L for 1. Very few actual elements, or actually compounds, are found as a liquid in chemical reactions, so it's very rarely used. A solid is used very frequently, and also the gas. And the reason why liquids aren't used very often is because most of them are actually seen as a aqueous solution. And this designates the AQ, meaning that it's based in water or dissolved or dissociated in water. And that water is just kind of the carrier, the housing of where everything is occurring. And so that's the AQ for the aqueous or aqueous solution. The delta above there means that heat's being supplied in some fashion, and that will we do look at some of those reactions as well. And the platinum at the end is something that is used to indicate that a catalyst is done. And the catalyst is usually a platinum-based catalyst. And you can think of a catalyst as a swift kick in the rear to get the reaction going. Now, one of the basic understandings, one of the basic laws of chemical reactions is based on the law of conservation of mass, given to us by the father of chemistry, Antoine Lavoisier. Antoine Lavoisier gave us the law of conservation of mass. Basically what comes from that is that we must have the same mass on both sides of the equation. The total mass of the products must equal the total mass of the reactants. Now, we also know that atoms cannot be created or destroyed in a non-nuclear process. So ultimately, Antoine Lavoisier's law of conservation of mass says in a non-nuclear reaction, matter cannot be created or destroyed. So what we're going to do is everything has to be accounted for. Therefore, if we have 2 carbon on the reactant side, we have to have 2 carbon on the product side. Now, one of the things that a lot of students like to do when we do chemical reactions is, because it might make life easier to balance it, is just to add a couple extra hydrogen or oxygen there, that we can't do that. And what's going to drive this is that what we're going to look at is what's called balancing chemical reactions. And we need to make sure that we have everything balanced on both sides of the reaction. Atoms in a chemical reaction do not change, but are rearranged. True or false? So let's look at this, re-examine our equation from before. Now, to understand whether or not it's balanced, I highly suggest using this method. When I was in junior in high school, many years ago, they never really gave us any tools. They just said start counting and making sure that everything balances out, and start putting coefficients in front of the compounds to determine whether or not it's balanced. That worked fine for some, but that doesn't work well for others. And what works, I think, a little bit better is this other method. And that's usually kind of making an accounting chart almost. And you have an R for your reactants and a P for your products. And you make a little accounting chart. And so you start writing down the elements as they're written on one side, because if it's on the reactant side, it has to also be on the product side, and so we can't just add things anywhere. And so I can see that by just writing out, I also have sodium hydrogen carbonate. I have a sodium, I have a hydrogen, I have carbon, I have oxygen. And if I look at my acetic acid, I have a hydrogen, a carbon, hydrogen, oxygen. So everything is taken into account. And so now I count how many sodium do I have on my reactant side? Well, I have 1. And then how many do I have on my product side? Well, I also have 1. Hydrogen, and now we have to be very careful to make sure that we look at every single hydrogen. I have 1 hydrogen here, 1 there for 2, and then I have 3 right there. Well, 2 plus 3 is 5. And then on the product side, I have 2 and plus 3. I also have 5. Now the carbon, I have 1. And then I have 2, which will give me 3. Carbon on the product side, I have 1 and 2, which will also give me 3. The oxygen, I have 3 plus 2 should give me 5. And then on the product side, they're spread out, so we have to be very careful. I have 2 plus 1 is 3, plus 2 others gives me 5. And now I can see from this that my chemical reaction is balanced, and therefore I do not require any coefficients in front of my reactants. So now let's look at a different one. As we see here, we can, right from the go, we can see that iron is not balanced, which means I'm going to have to balance this chemical reaction. We need to make sure that the number of iron on the reactant side is equal to the number of iron on the product side. The number of copper on the reactant side has to be the same on the other side. when it's important that we do this by only using coefficients. We are not supposed to use just starting to put numbers anywhere, because wouldn't it be nice, oh look, I have 3, to put a 3 right in the middle between my copper and my sulfate. That's not allowed. We can't do that. So what we have to do would be to put numbers as coefficients, and coefficients are big numbers that go in front of the actual compounds that we use. So what numbers go in front there? Well, let's make our little chart off to the side here. And that's what I need to do, is make my little chart. R, P, I have iron, I have copper, I have... Now one of the things I'm going to do is I'm going to have sulfate together, since it's together on both sides. I'm going to put it in parentheses so we can identify that it's the whole thing, everything that's inside there. I'm going to see that I have 1 iron on the reactant side and 2 on the product side. I have copper is 1 and 1, but my sulfate is 1 and 3. Now some people might start looking at this going, I don't know where to start. Now it really does not matter where you start. As long as you progress through and in the end get all of your reactions to balance out, you should be good, and it should be okay. So some might start, I would highly suggest actually balancing out things that are by themselves last. But you can start wherever you want. I'm going to start with putting a 3 in front of the copper 2 sulfate. Well, that changes my sulfate now to 3, but now that changes my copper to also 3. And you might be thinking to yourself, Mr. Peterson, why did you do that? Now copper's not balanced. Well, copper is actually very easily then balanced by putting a 3 in front of the copper on the product side. And then I can come back and I can balance out my iron by putting a 2 in front of the iron on the reactant side. And now, after I redo my chart, I can see that my reaction is balanced. The law of conservation of atoms requires that in a chemical reaction equation. So, practice, practice, practice. Let's get going. So, balance the following equations. And again, I'll make my chart. I'll probably have to erase my chart a number of times to fit everything in, but we'll make it nonetheless. So I start off with, this time I only have 1 reactant. Well, that should mean I want to leave that alone as much as possible, because anything I do to that 1 reactant is going to indicate that things are going to change. And so I have 1 sodium on one side, 2 on the other. I have 1 hydrogen on one side, and then I have 2 on the other. I have 1 carbon, but then on the other side I have my carbon are split up, so I have to be very careful about looking at them, but I have 2. My oxygen, I have 3 on the reactant side, but I have 3, even though they are spread out, I have a total of 6 on the product side. Well, now this reaction actually makes life easy, because I can see that everything on the product side is double that of what I have on the reactant side. So I can put a 2 in front of my sodium hydrogen carbonate on the reactant side. And now my reaction is balanced. I have a 2, 2, 2, and 6. And now, because everything is balanced, everything is okay. The next one, I'm going to write out another reaction chart here. Let's see here. Get the right pen going. I'm going to have my reactions and my products. I have iron, I have chlorine. Ooh, this is going to get really crowded really fast. I'll write that in a different location, I think. Write it out. As long as it's written out, it should be okay. I'm going to have my reactants, my products, iron, chlorine, silver. I'll need to make sure I erase this, not to confuse it with the last example. And I got sulfate together on both sides again, so I'll keep it together. Hopefully. When I look at my reaction, I can see that it's not balanced. I have 1 iron on the reactant side, 2 on the product. Chlorine, I have 3 and 1. Silver, I have 2 and 1. And then sulfate, and be careful with sulfate because a lot of people want to say that you have 4, but you only have 1. And then on the product side, we have 3. So that's why we put that in parentheses so that we can identify how many we actually have. And now for this one, it can be a lot of fairly daunting because you're going to look at it and go, oh my gosh, I don't know where to start. My suggestion, okay, well, if you don't know where to start somewhere. You have to start somewhere. Best thing to do, let's balance out our iron. Start with the first one. Who cares? So I start off with that. That changes my iron to 2 and my chlorine to 6. Don't go trying to balance out your chlorine right away. You can, or maybe you want to. It doesn't matter. If I balance out my chlorine, the only way I could do that would be by putting a 6 in front of my silver chloride. By putting a 6 in front of my silver chloride, that means that I have 6. Well, the only way to balance out my silver on both sides would be by 3, because 2 times 3 is 6. Well, that changes my silver to 3. Also, that ends up changing my sulfate to 3. So, lo and behold, my sulfate balance out. Yay! And everything is good. Notice not everything gets a number. Things to check for when you're looking at these are all my numbers non-divisible by each other, or non-divisible by 2. 2 and 3, well, you cannot divide 2 by 3. You can, but it gives you a half. And you can't go halvesies on any of these things. So no partial numbers, all whole numbers when we're looking at that. Now I'm going to erase this chart here before I get going on the next example so that we can see. And what I can see now is I have 2 hydrogen, chlorine and chlorine, just kind of looking at this and trying to see, do I even need to balance it? And I have 2 and 2 and 2 and 2. Everything is balanced in this last example. And that happens, and that's okay. Sometimes we enjoy that it happens. That means we don't have to balance it. Another example, we have our silver nitrate reacting with iron 3 chloride to make silver chloride and iron nitrate. Well, just like before, I'm going to make my chart. Hopefully I remember to write it out the correct way this time. And I can see I got a silver. My nitrate's together, so I'm going to put it in the same thing I did with my on the other side. Iron and chlorine. Ooh, getting a little crowded. My silver, I can see that I have 1 and 1. You might be thinking, well, why did you do it? Well, if I look at my nitrate, I have 1 nitrate, not 3, because everything that's there is just 1. And then I have 3 on my product side. Iron, I have 1 and 1. And then my chlorine, I have 3 and 1. And now this one becomes quite the conundrum. And you think, well, how can I do this? Where do I start? It doesn't matter where you start. Start by balancing out your nitrate. What do you need to balance out your nitrate? Well, I need to balance out my nitrate. I need to, put a 3 in front of my silver nitrate on my reactant side. But now my silver isn't balanced out. Well, if I look at my silver chloride, I need a 3 there. Now that 3 balances out my silver, and it also balances out my chlorine. And that makes everything balanced. Now in the last problem here, we have a little bit more going on. And because it's all words, and some people are going to go, oh no, what do I do? Well, this comes back as to how good did you pay attention during the naming unit. And that's usually what happens, is how well did you pay attention to the naming unit. So, barium chloride, well, I know what barium chloride is. That's BaCl. It's aqueous, which means it gets an AQ, but there's something special about this, is that barium is a +2 charge, and chloride has a negative charge. Do those charges match up? No, they don't. Therefore, you need to do your crisscross method to do that. So now it comes into important that we can see, literally and figuratively, that we need to pay attention to those charges that we were trying to have you pay attention to in the previous unit, and whether or not they matter. Well, it matters when it comes to balancing the chemical reaction. The next one, we have a chromium 3. Ooh, that 3, that probably means that I have Cr3. Well, my anion is sulfate. That's SO4. Do those charges match up? They don't. Therefore, I need to do my crisscross method before I even write it out as Cr subscript 2. Then I have my sulfate, SO4, if I write that out correctly. SO4. Outside the parentheses goes the 3 because I have a total of 3 sulfates. And that is also aqueous. I should make sure and indicate that. Arrow. To produce solid barium sulfate. Well, I have those written out there, and that should help me out to see, do I have, in my barium I have a +2, sulfate I have a -2, so therefore when I write out my products, I don't have to do any crisscrossing. It's a solid, meaning it's found as a precipitate in some fashion. And to make a chromium 3 chloride. Well, if I look at my ions there, I can see that chromium has 3 and chlorine has 1. I'll have to do the crisscross method to get CrCl subscripted 3, and that would be an aqueous solution, even though not indicated to us. Now we have to ask ourselves, is it balanced? No, it's not. So I'm going to just piggyback off my chart that's up top in the corner here and see that I have a barium, I have a chlorine, I have a chromium, and I'm going to use the sulfate in parentheses since it's on both sides. I have 1 barium on one side and 1 on the other side. I have a chlorine 2 on the reactant side and 3 on the product side. Chromium I have 2, and then on the product side I have 1. Sulfate I go start with 3 and end with just 1. And we're like, oh no, what do I do? Again, start balancing somewhere. Does not matter where. Some people might start balancing out their chromium. So they put a 3 in front of their chromium chloride. Chromium 3 chloride, excuse me. And so that changes that, and then it changes the chlorine to 6. And then they might go, well, I also need to balance out my sulfate. My sulfate will need to balance out by putting a 3 in front of my barium sulfate. By putting a 3 in front of my barium sulfate, I now have 3 sulfate and 3 barium on my product side. Now it balances out the sulfate from the reactant side, but my barium still needs a 3 on the reactant side. So in front of barium chloride, I put a 3. But that also turns around and balances out my chlorine. And then everything is balanced out as we have it written. What coefficient for sulfuric acid is required to balance out the following equation? Water-based solutions are indicated by which symbol?